All right, hello class. So what we're doing today is I'm going to walk you through the exercise I want you to do that's taking place of the class that we're missing today on Thursday because of the storm. So what we're talking about today is estimates, or something called a Fermi estimate. Basically, the idea is how do you make an estimate of a value when you think you maybe don't know enough information to do it. This is called a Fermi estimate, named after Enrico Fermi, who's famous for doing this. So this is Enrico Fermi here in the middle. He was made famous because of the Manhattan Project, which was the development of the nuclear bomb during World War II. So Robert Oppenheimer, who you may have heard of, he is here on the left, and then Lawrence is here on the right. These guys were all in the Oppenheimer film. Fermi was the guy who was working on the chain reaction up in Chicago. He's quite famous for this, and there's actually a big national laboratory where people do research called Fermi Lab in Chicago, named after him. So why is it named after him? So the basic idea here is that sometimes you don't know enough information, but you try to make a best guess of a value. And usually the best guess is within a factor of 10. So is there 1 of something? Is there 10 of something? Is there 100 of something? This is called an order of magnitude. How big is something? Sometimes that's all you can get. But knowing that there's 100 of something instead of 1,000 of something is actually quite valuable in terms of information. The reason these are named for him is he was famous for doing this during the Trinity test, the test of the atomic bomb in New Mexico at Los Alamos. So basically the idea here, this here is his kind of record of what he saw. And I'm not going to read the whole thing here. This will be posted later if you're interested. But if you remember the movie, what happens is that they're testing the explosion. And everybody's facing away from it because they don't want to see the explosion. They don't know if it's going to hurt their eyes. But what he did is he took pieces of paper and he dropped them right when the shock wave of the explosion happened. And what happened is the piece of the paper, the shock wave pushes them. So he dropped pieces of paper and he saw how far they moved. He knew how heavy the paper was. He knew there was no wind right now. You know the force of gravity. And so he was able to use that, plus his knowledge of nuclear physics, which you or I don't have, so we wouldn't be able to do this. But he was able to use that knowledge to make an estimate of the atomic blast and how strong it was. And he found that it was 10,000 tons of TNT. And when actually they went through and they did all the calculations with more information, they found it was about 20,000 tons of TNT. So he got within a factor of 2 of the strength of the atomic bomb just by watching a piece of paper move and making an estimate on called back of an envelope. But usually it's like a little piece of paper and you make little back of envelope calculations. So this is why it's called a Fermi estimate. So how do you do one? So this next slide shows you an example. It's actually a little bit more complicated than what I'll ask you to do for class, but bear with me. All the information's on the next slide. Usually I like to kind of draw it out and do piece by piece and ask students in person. All right, so the first one we're going to do, the one I'm going to do, is how many times you have to fold a piece of paper in half to reach the moon. So you just take a piece of paper and you see how many times you have to fold it in half to reach the moon. But we need to know a couple of things. First, we need to know how thick is a piece of paper. You could take a piece of paper and measure it if you had a really accurate caliper. If you don't, you could also stack 100 pages, measure that, divide by 100, or you can make a guess. So the idea here is you try to come up with numbers that are smaller and smaller until you know it's in the right range, right? So if someone said 1 centimeter, you'd say, well, a piece of paper is definitely thinner than 1 centimeter. If someone said 1 millimeter, if you think about a ruler, you'd be like, yeah, that piece of paper is smaller than a ruler, smaller than a millimeter, but it's probably not 100 times smaller than a millimeter. So what you would say is the upper bound is 1 millimeter, the lower bound is 1/100th of a millimeter, so kind of right in the middle is 1/10 of a millimeter, 0.1 millimeters, or 1 times 10 to the minus 4 meters. We'll go over scientific notation later in class. And that's actually, if you measure a piece of paper, that's basically how thick it is. So just by guessing, you can get there. Now you need to know the distance to the Earth to the moon. That's a little trickier, but we can still do the same kind of thing. So you could say 1,000 kilometers is probably too small. That's basically the distance from here to New York City. 10,000 kilometers still seems not far enough, right? If here to New York City is 1,000, maybe I give you that value. You would say the moon is more than 10 times far away than that. 100,000 kilometers seems maybe more in the right ballpark, and maybe 10 times that, 1,000,000 kilometers seems too far. So you kind of take the midpoint between those two. This is a hard one to guess. I'm going to give you guys a little bit ones that are easier to guess based on your everyday experience. So if we guessed 500,000 kilometers or 500,000 kilometers from here to the moon, you'd actually be pretty close. The actual value is basically 3.8 million kilometers, which is pretty close. All right, so then how many, those are the two Fermi estimates. This last little piece is kind of just a fun little calculation. You have to divide how many pages would fit if we stack them together. So basically, if you divide the two numbers, how many pieces of paper do you have to stack in a row to reach the moon? It's 4 trillion pages. That's a lot of pages. So that's not going to happen. But now how many times do you have to fold it? We're talking about folding the piece of paper. The important thing that's folding a piece of paper is that each time you fold it, you double the thickness of the paper. So that's this equation here, which I'm not going to ask you to do anything with this equation, but that just says the thickness of a piece of paper is its original, folded, is its original thickness times 2 to the power of how many times you fold it. So that makes sense. If you fold it once, n is 1, so the new thickness is the original thickness of a piece of paper times 2. Then if I fold it again, it's times 4 because you double the whole thing, and so on and so forth. Because this is a power law, it grows really fast. So here are some calculations that basically says, I just say, try some numbers. And what you find, and you can use a spreadsheet to do this, is you have to fold the paper 42 times to reach from here to the moon. That might seem like a really small number, and it is, and it's kind of remarkable. It shows you how powerful things scaling at this factor of 2 are. But it's almost impossible. You can try it yourself with a piece of paper. This old program, The Mythbusters, that was on television here, they tried to do this. And I think they couldn't get more than 8 times. There's kind of an old tale that says you can't do it more than 7. So I'm not going to be asking you to do any of those calculations. But what I will be asking you to do is do an estimate like we see here. How thick is a piece of paper? So if you go to Canvas, you will find, if you go to the assignments here, this is a participation grade because this is basically instead of being in class. It's an estimations activity. So here's the activity. You're going to have to scan it with your iPhone Notes app or Cam Scanner. Please take like a PDF or a JPEG. Don't upload native iPhone images. I can't read them. And so what you're going to do is you're going to look at this document. So let's just download it real brief, and we'll take a look at it. So here it is, estimation. We're going to do estimation activity. So example, I do more example here. So for the first one is the length of a footstep. What's the upper limit? And you try to use, actually you can use whatever units you like. You could use inches or you can use meters, whatever you're comfortable with for this assignment. So length of one footstep. 10 meters is probably too big. 1 meter is probably right around the right ballpark, and 1/10 of a meter or 10 centimeters is probably too small. So what you want to do is pick an upper limit. So if it was a footstep, you'd say 1 or 10 meters here. A lower limit would be like 1/10 of a meter, and then pick the midpoint. What it says 1 to 2 significant figures here. Don't tell me it's 1.2576 meters. You don't know that much information, just kind of round it. Then look up. Once you've done this estimation, don't use Google at all. Look up the actual value and then comment how close are you. Did you get super close or not? So, weight of a giraffe, is the giraffe maybe 10,000 pounds is too many? Is 1,000 pounds too many? I'm not sure. And then think of the lower one. 1 pound is too small, 10 pounds is too small, 100 pounds is too small, 1,000 pounds? I don't know. And so then you pick the midpoint. Then you look up an actual value, and then you're going to comment. So we're going to do, there's a distance, how wide is a human hair. You're going to do a couple of these, just fill this out. Make sure you include units on each of them. Tell me how many, what you're looking at, and then you'll upload. I want everyone to remark upon the weight of the giraffe. Make sure you keep that value, and then we'll go over that as a class on Tuesday. So I hope this is an interesting exercise for everybody. It's going to show you how powerful just guessing can be, even if you think yourself is not a scientific or mathematical person, you'll probably still get closer than you think. Feel free to work on this with a friend or so, or you can work on it alone. And I will see you next week.